Hello and welcome here to this webinar about thermocouple measurement with Beckhoff components. My name is Martin Podrouschek. I'm working in the product management AO of Beckhoff here in Germany. And we will see now in the next 30, 40 minutes some information about thermocouple measurement and how to do that. If you have a question during the webinar, please use the question window, and then in the end we will see what we can answer of your questions. Today in this presentation, we will see a little bit information about thermocouples. We will, of course, not go in all theoretical deep, but just that what we need here for our industrial use of thermocouple measurement. We will have some overview over Beckhoff thermocouple devices. You see here the TC. I use this short for the thermocouple name. So we will see here an overview over this Beckhoff thermocouple devices of the different series, EL, ELM, EP, EG, whatever, and how fast and how accurate they can measure. I have done a small video here for a demonstration of fast and precise measurement. We will have a look at Beckhoff thermocouple specification in detail, and in the end, some practical hints about thermocouple usage on a real application. When we want to measure temperature at all, we have different possibilities on the world. I think the two most used are RTD sensors, resistive sensors, and thermocouples. Resistive sensors, PT100, PT1000, are easy to use. They have some issues, wire resistance and so, but things that are good to solve, but they are not in focus here of this presentation. One point can be that a milliampere current that may hit the sensor, but these are things that can be good solved here with the Beckhoff RTD products of the series 32, EL32 or EP32, ELM32, or with the multifunction terminals of the 37 series. The big point here in this presentation are the thermocouples. We want to focus today on the thermocouples. That's not so easy to measure because of the millivolt measurement. So they are sensitive for interferences, maybe. And the big point is here the cold junction temperature measurement inside of the terminal. But this will we see later. We have a lot of products for these thermocouple measurements, especially the 331 series of EL, EtherCAT terminals, K-bus terminal, EP, EJ, whatever, or also with the multifunction terminals of the 37 series. The other principles, fiber bragg, some infrared measurement, optical way, is not here in this presentation. So we focus here now on the thermocouple measurement, which is often used in industrial area. The thermocouple itself is in the beginning of the measurement chain. It is a sensor which is then connected to the measurement modules, devices. Here in the picture shown the ELM devices. But also other devices like EtherCAT terminals can be used, or the EG modules. And then the information goes over the EtherCAT as a Fieldbus to the software on premise, so locally or in the cloud, whatever. So this is the thermocouples are part of the measurement chain, and we will now have a look how this thermocouple itself works roughly. We see it here in the drawing. A thermocouple consists of two wires of different material, metal I, metal B. And here on this point, they are shorted. And over the length of the wire, it generates, caused by the temperature difference, voltage. A potential difference is then to see here between these 2 points. So this point at all is called the cold point, the cold junction point, CJ. Also called the reference point, or there are different names for this point. This point is here inside of our measurement device. And on this point, we have a temperature. This is very important. and we have a millivolt voltage that we can measure here, the thermo voltage, UTH, between these 2 points. And what we are interested here is the point here. It's the so-called the hot point, the process temperature, the measuring temperature. We are interested to measure the temperature here on this point. And the thermocouple, the 2 wires here, they give us the information about the temperature difference between the cold point and the hot point. So when we know the temperature on this side and when we know the millivolt here, then we can calculate the temperature here on this point. So we look for the temperature of the hot point, very accurate, hopefully, and we know the temperature of the cold junction point. Most times this is inside of our temperature measurement device, and we measure the millivoltage of the generated potential that comes out here from the thermocouple. And of course, the thermocouple can measure it on a lot of other ways also, with ice bait and 0 degree bait and so. But here we are focused here now on the industrial way, as it is done in the most electronic thermocouple devices. They have electronically compensated cold junction circuit, as we see here. So this is now in the focus for the next sheets. So what happens here now inside of the device? We have the temperature that we want to measure, and we have the thermocouple as a sensor, and this thermocouple is here connected to our measurement device. So at the first, we measure the millivolt with a voltage measurement inside the device, and we have to know about the cold junction temperature in the device. So we have 2 measurements. We measure a temperature and a voltage. Because of the basic rules for the thermocouple transformation, we have to transform this temperature into a voltage, and then we can add these both voltages and make a retransformation from voltage to temperature. And in the end, we have here the result of the desired measurement temperature, T measured here, which hopefully is the same as here the temperature which is applied to the sensor. And this information goes then in most cases over EtherCAT to the controller, to the logging system, whatever. And of course, this measured temperature must be compared to the desired accuracy of this process. So how accurate should this measurement be? How low should be the uncertainty of this process be? Because we see here some influences into this box. The small point is the mathematic transformation accuracy that goes here and here into the accuracy. A bigger point is the point of the accuracy, the uncertainty of the voltage measurement. How good is the millivolt measurement here of the thermocouple? And a very big point is the accuracy of the cold junction temperature measurement. So how exact can the temperature of this point here when the metal changes from thermocouple to inside of the module. So this is the cold junction point here. And this is the point where we need the inside temperature. And this must be measured very precise. And overall, we have here an electronic device. And so we have also ambient temperature, which influences our electronic circuit and maybe changes there some characteristics. So a lot of effects that goes into this thermocouple measurement module, and we have to care about all of them. So let's have a look which devices, which applications need a thermocouple at all. Thermocouples have very strong advantages. So they are cheap. So they are often you can buy them for the most of them they are cheap. So when you have a measurement application where you think that your sensors will be destroyed because a gearbox is in an overload test, for example, then it's not so bad as if you use RTD sensors, which often are more expensive. Thermocouples are very fast. because thermocouples can be created very small, smaller than RTD sensors. Of course, you can mount thermocouples also in a big iron pipe, and then they are bigger. But the thermocouple itself is very small, and so it can react when it has no big housing very fast on temperature changes. So it's good for fast process like brake testing or welding processes. So it's very fast. There's a big advantage. Resistances of the wire have nearly no effect today because the input resistance of the thermocouple devices of Beckhoff, for example, have a very high input resistance, and so we don't have to care here about any 2, 3, 4 wire connection or up to 6 wire like a strain gauge sensor. So this makes the cables also cheap. This is good for us. Also a good point is the thermocouple can measure very high temperatures, up to 900,000 degrees. And over this, only thermocouple is possible. So when you have to measure high temperatures, you have to use an optical way, infrared maybe, or you use a thermocouple. But there are some disadvantages because we have here a millivolt system. We have maybe big influence of disturbances. And so we have to think about shielding and grounding if we use thermocouples. Aging is a big point because thermocouples always drift and age over the time over hours, over years. And this may result in big measurement errors after 2,000, 5,000 hours. 10,000 hours is just 1 year. So it can be that maybe the drift of the thermocouple is some 10, some 100 degrees. And the cause for this is the mechanical stress. And mechanical stress and also fast temperature changes are not good things for thermocouples. So when you use thermocouples, you always have to think about what happens in the next months, and maybe you have to check regularly this thermocouple. Thermocouples itself are not so precise as RTD are. So we have bigger accuracy class. For example, at type K, it's just plus minus 1.5 Kelvin or degree. So this is a point when we are interested in very high precision measurement, then thermocouple is maybe not the first choice. And a very big point is that thermocouple measurement itself is very sensitive for any transition. So connectors, switches, or something that is on the way from the hot point to the cold point can generate locally some millivolt or microvolt thermo voltages, and this can false away your complete measurement. And this is also dependent from temperature and time. So it's a very bad thing that there are false microvolts generated on the way because maybe you are multiplexing the device or you use the wrong multiplexer, and this can make your complete measurement damaged, like it's shown here in this icon. So we see here that in the Beckhoff devices or in the thermocouple devices at all, we have to measure very accurate, that is with a low uncertainty, the millivolt and the cold junction temperature inside. And we have to think about a stable thermal situation inside of the device after power on state, for example. And also the outside situation, the ambient temperature should be stable and not changing very fast, because all of this may increase the measurement uncertainty of your thermocouple system. Aging is a big point. We have to think about noise. And on top of this, of course, came the uncertainty of the thermocouple sensor itself. And additionally to this, between sensor and Beckhoff device, you have some extension cables. This may also bring some additional error. Let's come into figures. We have some thermocouples noticed in the standards. Here, for example, in the EN standards, the BCEGK, for example, K, the most of us know this nickel chrome nickel sensor. I think it's the most used here in the world. It creates some 40, 50 millivolt of voltages. The green, white is the coloring. I think you have seen that. And all of these transformations are integrated, of course, in the Beckhoff devices for using this as a thermocouple. And you see here also a list of the transformations which are integrated in the ELM37 module, not only the one from the standard, but also additional one here, the A standards from Russia, and some platin thermocouples. So we think we have everything covered that worldwide is used as a thermocouple sensor. Now let's go into the theory, our way on the to the goal of the Beckhoff thermocouple specification. What have we to care about? There is on the first point the thermocouple itself. You see here the different types. The B, C, A, and K is the green one here. So you see they have different temperature ranges, and they are all referenced to the 0 degree point here, where they have no voltage here, because thermocouple is always a differential temperature measurement system. But you see here that we have here no linear behavior. We have here, especially in this area here, we have here a problem. We have to use many points in our firmware to make a good assimilation for this specification of this characteristic. So this is the first point that we have to cover on the different TC types. The second point is that, of course, the internal cold junction measurement has an effect inside of the module. And the second point is that the millivolt measuring on this area, where we have small voltages of the thermocouple itself, becomes higher and higher because we have an absolute millivolt measurement in the modules of 30 millivolt or 70 millivolt. And when the millivoltage goes down, then the relative uncertainty goes up. And this makes then altogether the effect that the characteristic of a thermocouple measurement based on all of these points is like this. It's a very spectacular characteristic. And we are not on the end, unfortunately, here shown here for this type K. This is only the characteristic for 23 degree. And so we have an effect of the ambient temperature on the electronic device. And when we here now see the line for the 55 degree ambient temperature, which is often the maximum temperature of a Beckhoff device or of some EtherCAT terminals, then we see here the red line that we have here additional error measurement deviation here. I would say that comes around here at the type K in this terminal EL314. We have additional 0.5 Kelvin additional uncertainty when you use the complete ambient temperature range of the Beckhoff terminal. So the ambient temperature has an effect, and unfortunately also this effect is nonlinear. You see it here in the green line. 39 degree is the middle between 23 and 55, and hopefully the line is in the middle here between red and black, but you see it is not. So we see here it is a nonlinear effect, but anyway, we in Beckhoff think that these plots give you as an user for thermocouple measurement very deep information, very detailed information that you can take these plots and then see for your application at your measurement point, at your ambient temperature, what is the final uncertainty that you can see when you use our Beckhoff devices here using thermocouple measurement. We see here the characteristic of a type K. Or we have seen that there are different types. Just for example here, this is the type C on the same terminal, and you see it has a complete other behavior. We have here nearly 6 degree deviation or uncertainty on the 0 degree measurement point. we have here the optimum at or something around 500 degree. And when you use the thermocouple, then here now at the 2200 degree point, you have nearly 10 degree deviation here. So that is now a problem for good and for a fast decision which thermocouple system I should use. And so we in Beckhoff have chosen a very practical way how to get here a good specification value. And so Beckhoff defines recommended range for each thermocouple type. So this is a Beckhoff choice to say clearly. It is a reduction in the range for industrial use. And inside of this range, we expect that the most of our customers are working. So you see here the type K. Type K is specified in the norm, in the standard from minus 270 to 1372 degree. You see it here. And we in Beckhoff say that there is a recommended range, which is a subset from this. It's from minus 100 to 1200 degree. You see it is this. And I would say that this is the area where the most customers are working when they are using type K. I think the most applications do not working at minus 200 degree, or when they are working in this area, maybe then they do not use the type K. Whatever, when they do, then they are fully supported here in the Beckhoff terminal. It's just to get a good specification value that you can easily select the thermocouple for you. And so when we know this, then we can here now have a deep look into this type K on this terminal. And we see here, let's choose here the red line. It is the 55 degree characteristic of the type K. And we make here a red line here, and we see it's something around 1.1 degree uncertainty. And this is the value that you find here now in the Beckhoff specification. When you're using your device up to an ambient temperature of 55 degree, then you have the basic uncertainty, and you have the thermal temperature coefficient of the module. And in the end, with the type K, you have then uncertainty of plus minus 1.1 Kelvin, or also here calculated in percent of full scale value. But this is more the practical way. You can very fast see which thermocouple gets which result on your module. So this is the Beckhoff way of thermocouple specification. I think it's a very technical way. Here on this side, you have a lot of information which module you can select, and you can choose your operating point that you have in your application. So, and this is done on our overview of thermocouple modules. You see here on the left side, we have here KL modules for K-bus. We have some EtherCAT terminals, ELM modules, IP boxes, and also an EtherCAT plug module. And this table here is organized here by these columns. We have which housing, number of channels, connection technology, which resolution have the modules, what is the maximum sampling rate, uncertainty at type K, very important to have that you can compare the values, which electrical millivolt ranges are inside, oversampling, is external cold junction possible with that module, is distributed clock possible, some applications need that, are the channels isolated, is TwinSafe SC, so our safety double channel system supported, is the what filters are inside of the modules, diagnosis, and some features. So that is the overview for you. You can see there on a very good in one picture which module can cover your needs in your application. And let me highlight here some points out of this table. You see here for the first, we have a module, our first module with the mini thermocouple plugs. We have modules with 1 millikelvin resolution. Several modules support this. We have very fast thermocouple measurement, up to 10,000 samples per second on each channel for high-speed applications. We have very accurate modules. You see it here. Our mini thermocouple module is the most accurate that we have at the moment. I will show in the next sheet then. We have a module with isolated channels, can be a good problem solver. We have modules that support the free filter design by the TwinCut filter designer, which is also a nice feature, which I show now. We have modules with condition monitoring observation, important point on industrial applications. And this terminal, for example, the ES3C14-010 is also available as a calibrated version with an ISO 17025 or DAX certificate. Especially this module here is very, very new. And so let me just show here to you. We have our first thermocouple measurement modules in the ELM series, the ELM 334 devices. They are part of the economy line, 1,000 samples per channel. Inside there are multiplexing, very high temperature stability, 1 millikelvin resolution is supported. Have inside the common mode voltage measuring for detecting earthing problems, for example. All TC types are supported, and they are available with these mini thermocouple connectors for absolute best results in accuracy. So what gives now this for results? We see here now on the first point the different accuracy ranges that we can cover here on the type K. Always have in mind that we are focusing here on type K. The other types are inside of the documentation. And we see here for the standard accuracy, we have standard terminals, EtherCAT up to 100 samples per second. Then we have a little bit more accurate devices, also in the slow area, something around 2 Kelvin uncertainty. And then we come here in the higher accurate devices and also combined with higher sample rate up to 1,000 or 10,000 samples per second for high speed measurement and also very high accurate measurement with a low uncertainty. That is the technical point, but of course we are also interested in the financial point, more accuracy, more speed. Also here means that the list price is higher. But to give you orientation, I have here this table inside. We see here that with a standard terminal with plus minus 3 degree of uncertainty at type K, we start here as a standard terminal. The high precision one has done the half of this uncertainty and of course has a little bit more price. And then we go into the ELM area, into the measurement terminals under 1 degree of uncertainty at type K. And you see there in the 4-channel version, this is the 4-channel version, this is the 8-channel version, we have then the appropriate list price on it. But just to give you an orientation, how much is the accuracy increased, the uncertainty is decreased, and what means that in the price in the end, that gives you an orientation. Can you use high precision thermocouple modules in your application? Is there the financial room for this? And just for orientation, a laboratory device, reference devices that also we in Beckhoff are using here, for example, for production, they are then in another price range. But of course, on the world it's possible. And when you need that, then these devices are on the world available. And now let's come to my small demonstration here. I have a video here that I can show you how fast and how precise we can measure thermocouples here with this ELM 37 multifunction module. So you see here a demo system that I'm using for my demonstration here. And we have here a thermocouple type K, which is mounted here inside of this small plastic housing so that the air is not disturbing. And the thermocouple is here connected directly to channel 1. And we have here a small LED, which is here connected to an EtherCAT output terminal. And I switch it on and off, and the light is here going over something 8 centimeters to the thermocouple. The LED has something around 700 milliwatt. And the thermocouple is very small, so I think there are just some microwatt that are really are arriving on the small thermocouple itself. But anyway, this thermocouple is warming up, and we can detect this very good here with our multifunction terminal. You see here now the video. You have here the webcam now, where you see here the light directly, which is then flashing here into the thermocouple. There is a small SPS PLC program from my side. And here on the right side, we have here the absolute temperature of the thermocouple itself. It's something around 19.9 degree. And here on this graphic, we will see then the LED flashing. And here I have calculated, I can start it now, the relative temperature change of this. So it's just an average over 10 seconds, because this is changing very much and not so easy to see. And we see now the LED is starting. So this is the first flash and the second flash, 150 millisecond. And you see that here the temperature is going on something about 20 millikelvin. So in the 150 milliseconds of the light, the thermocouple increases about 20 millikelvin. You see it also here. In the big jump, you see that the air in the device goes higher. So a very good presentation, I think, to show how fine we can measure thermocouple and how fast this thermocouple reacts here on the small light energy that arrives here on the thermocouple itself. So in the end now, I will show you two big points when you're using thermocouples. The one point are the grounding problems. Thermocouples generates only some millivolts, and if the thermocouple is grounded or earthed and the common mode area is left, then the thermocouple device, the terminal, can have a problem. Big measuring error may then be the result, and that is the reason why we also show in some of our devices that just 2 volt of common mode difference is allowed. What you can do there, or what you can do before this, that maybe you don't have problems, correct grounding of machine components so that the earthed thermocouples have the same potential. Maybe isolated thermocouples, maybe an solution so that there is no grounding problem. We have devices with galvanic isolated channels, like this terminal, that can be a good problem solver. Or another point can be thermocouple modules that observates the common mode voltage for themselves and give you a warning if something is not okay. So there are different solutions for this grounding issue. And the other point is long distance measuring. When the process temperature is far away from the device, what we can do. So first choice is maybe we want still use the internal cold junction measurement in our Beckhoff device. Then you can run the TC wire itself to the thermocouple device. But this often means then that you have expensive cabling because the thermocouple itself is then wired up to the Beckhoff terminal or Beckhoff box. You can use extension cables that are made from the same material. So same issue. It's a more expensive thing and bring some uncertainty, additional uncertainty in your system. The more common way, I think, is compensating cables. Key say cables here for type K, for example, they're not available for all types. And in the normal ambient temperature that as it is given in the standard, they have the same characteristic like the thermocouple material, but only in this area. And this is the point. You have to know what is the ambient temperature, and if this anyway, it gives you an effect on your system, and maybe you have some additional influence on your thermocouple system when you use these compensating cables. And the other point may be that you use an external cold junction point. So this is shown here in this graphic. So we have here the thermocouple device, and on this point, we want to measure the millivolt, for example, over the thermocouple terminal, but this point is not inside of this thermocouple terminal or thermocouple box. It is outside. It is external. And so we need to measure the temperature here by an RTD sensor, PT100, PT1000, whatever, and measure this separately by another device. and give this information then here into the firmware of the thermocouple device. And this is supported, as you have seen in the big table, by most of our products. And is often chosen when you have here some external installation of your cold point. And the other point, of course, can be that this dual channel measurement of millivolt and of ohm is done in the module itself, like in the EP box or in some ELM modules, where the RTD sensor, the cold junction sensor, can be mounted inside of the plug or a little bit externally with some copper extension outside. So these are practical possible ways that some of our modules can be combined. So let's come now to the end and the conclusion. We have seen now that when we use thermocouples, then we have a lot to think about shielding, grounding, any thermal stabilization, what is happening after the power on time. In every documentation of thermocouple devices, you will find some warming up time, 30 minutes, maybe 60 minutes. You have to pay attention on permanent stable environment outside of the thermocouple device and on the cables. Aging is a big issue. Maybe you have then to calibrate and recalibrate regularly your system. And the problem of discontinuity on the wire, plugs, switches, anything that bring some micro voltages into your system. And in the end, it falsifies your measurement value. But when you all these points have in your mind and you think about it, then with the Beckhoff thermocouple devices, you have a very good system, very good components that can measure the thermocouple itself in a very good, accurate, and exact way. I'm happy that you have been here and listened to this webinar. Maybe we'll see us again in a next webinar here from Beckhoff. Have a good day.